ちが一つ。久しぶりだな。
Assalamualaikum warahmatullahi wabarakatuh. Today I would like to present the project presentation by the group Sharingan. I will start first, but for the topic is for our group is effect of heat transfer on the performance of an air standard diesel cycle. So let's introduce our Sharingan's member, which is Aminuddin Fitri bin Zailan, Muhammad Haziq bin Salmizi, Muhammad Fadli bin Sabar Bananti, Raja Amirul Ashraf bin Raja Hafiz, and myself, Muhammad Ahmad Akhtar bin Abdul Razak. So these are the project that have been accepted from our proposal. So this paper presents a thermodynamic analysis of an air standard diesel cycle. It presents the effect of heat transfer on the net work output and indicated thermal efficiency of the cycle. The heat losses through cylinder walls are considered to be proportional to the average temperature during heat addition process. And also the effect of other parameters in conjunction with heat transfer, such as cut-off ratio and intake air temperature, were also reported in the proposal. So what is diesel cycle? So diesel cycle were found by Rudolf Christian Diesel itself, which the diesel itself were named by him, Carl Diesel. The diesel cycle is a combustion process of a reciprocating internal combustion engine. Fuel is ignited by heat generated during the compression of air in the combustion chamber, into which fuel is then injected. This is in contrast to igniting the fuel-air mixture with a spark plug, as in the Otto cycle engine. The diesel cycle is assumed to have a constant pressure during the initial part of the combustion phase based on V2 to V3 from the PV diagram. It shows that diesel do have an increase in pressure during this period, but it's less pronounced than in the Otto cycle. So the idealized Otto cycle of a gasoline engine approximates a constant volume process during that phase. The diesel engine is a heat engine. It converts it into work. During the bottom isentropic processes, energy is transferred into the system in the form of work, which is W in. But by the definition, isentropic, no energy is transferred into or out of the system in the form of heat. During the constant pressure process, energy enters the system as heat, which is a Q in. During the top isentropic processes, energy is transferred out of the system in the form of W out. But by the definition as isentropic again, no energy is transferred into or out of the system in the form of heat. During the constant volume processes, some of energy flows out of the system as heat through the depressurizing processes, which is Q out. The work that leaves the system is equal to the work that enters the system plus the difference between the heat added to the system and the heat that leaves the system. In other words, net gain of work is equal to the difference between the heat added to the system and the heat that leaves the system.
Assalamualaikum warahmatullahi wabarakatuh. My name is Raja Amirul Ashraf bin Raja Hafiz, and I will explain about the schematic diagram. Okay, during this process, we need to consider it as a air standard assumption, which is the first assumption is air circulated in a closed loop. For the second one is consider it as a closed system. The third one is certain process is well insulated, and for the last one is consider it as quasi-equilibrium. Okay, as you guys can see, there is two graphs, which the first one is the PV diagram that shows changes of pressure and volume, and for the second one it is the S diagram that describe temperature and entropy change. Okay, so there is four processes during this diesel cycle, and the first one is called isentropic compression. It is isentropic because during the process, S2 is equal to S1, and it is compression because the volume decreases from BDC to DDC, where the piston will move upward and the piston will compress the air inside the cylinder. The pressure and temperature will also increase. For the position of the piston, it starts from BDC to TDC. Okay, for the second process is P constant heat addition. This is because during the heat addition process, the pressure is constant, where P2 equal to P3, and we have heat addition process that represent by Q in. We also have a expansion process because during this heat addition process, at the same time the piston will move downward for the expansion. Due to the increase of pressure and temperature, the air will also expand. Okay, for the third process, it is called isentropic expansion. During this process, the value of S3 is equal to S4, and the piston will still move downward for the expansion process, which it will move from TBC to BDC. The volume will increase. Okay, for the final process is V constant heat rejection. During this process, this piston doesn't move and the volume is constant. Because it have a Q out heat rejection to the surrounding, the temperature will decrease and the pressure will also decrease. Okay, I think that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Aminuddin Fitri bin Zailan and my metric number is B0420200027. Okay, for my part, I will explain about the method of performance analysis in this journal. As we can see from the slide, there are three methods of performance analysis that were used in this journal, which are diagram, equation and graph. For diagram, the PV diagram for the thermodynamic process performed by an ideal air standard diesel cycle was sketched to determine the process that involved in ideal air standard diesel cycle. For process 1 to 2 is isentropic compression process. For process 2 to 3 is heat addition at a constant pressure. For process 3 to 4 is isentropic expansion process, and finally for process 4 to 1 is heat rejection at a constant volume. Okay, for the equation, there are 6 equations that were used to calculate the data in this journal. The first equation is used to find the T2. The second equation is used to find the T4. The third equation is used to find the heat added per unit mass of the working fluid during the constant pressure process. The fourth equation is used to find the net work output. For the fifth equation is used to find the thermal efficiency. And the last equation is used to find the optimum or maximum value for the net work output. Lastly, for the graph, after the data were collected by using the equation that I mentioned before, the graph were plotted. There are two graphs that plotted in this journal. The first graph is plotted to determine the effect of B on network output and thermal efficiency performance, and for the second graph is plotted to determine the effect of A on network output and thermal efficiency performance. That's all for my part. Thank you.
Now I will emphasize more on the calculation used in journal paper. The condition used in this journal paper is constant specific condition, so we didn't have to refer to the ideal case table of air. So the first calculation is the work output per unit mass, which is W equals to Cp, or constant pressure, times T3 minus T2 minus by Cv, or control volume, times T4 minus T1. The second one is the heat addition per unit mass, which is given by Cp, constant pressure, times T3 minus T2. And the third equation is the thermal efficiency, which is given, which is which can be defined by 1 minus A plus times Cp minus B times R k power of k times R power of k minus 1 minus Cp plus B times T1 divided by k times A minus 2B T1 Rc power of k minus 1. To find the absolute temperature, T1 is given in the journal paper. To find the T2, we can use the equation T2 equals to T1 times Rc, or the cutoff ratio, power of k minus 1. K is the specific heat ratio, which we can find by dividing Cp with Cv. To find T4, we can find by the product of T3 times R over Rc power of k minus 1. To find the compression ratio, we can use V1 divided by V2, and to find the cutoff ratio, we can use by dividing V3 with V2. In this journal paper, the researcher considering the heat loss in the diesel cycle. So there are two new constant introduced, which is A and B, which are related to combustion and heat transfer. So the modification made into the calculation is during the heat addition is where Cp is replaced by A minus B times T3 plus T2. So to find T3 from this equation, we derive it into this equation, which will be T3 equals to A plus Cp minus B times T2 over Cp plus B. And if we derive more, we will get A plus Cp times Cp minus B times T1 Rc power of k minus 1 divided by Cp plus B. To find the T4, if we use the constant A and B, the equation will be A plus Cp minus B times T1 Rc power of k minus 1 divided by Cp plus B times R over Rc power of k minus 1. So after the constant is being replaced in these equations, finally the work output calculation will also be derived into much longer equation from this T3 and T4 calculations. So from W equals to Cp times T3 minus T2 minus Cv times T4 minus T1, it will become W equals to Cp times A plus T1 Rc power of k minus 1 times Cp minus B minus T1 Rc power of k minus 1 times Cp plus B minus Cv times A plus T1 Rc power of k minus 1 times Cp minus B times with R over Rc power of k minus 1 minus T1 times Cp plus B, and we'll divide it with Cp plus B.
Assalamualaikum warahmatullahi wabarakatuh. So now I would like to discuss about the suggestion to increase the performance of air-surrendered diesel cycle. So the first thing that we need to know is to increase the performance of air-surrendered diesel cycle, we have to increase the efficiency of the engine itself. So the thing that can be done is by higher compression ratio. So here we are limited by autoignition of the gasoline. That is, if the gasoline engine compression is above about 10.5, unless the octane number of the fuel is high, knocking combustion occurs. So this is annoying, and also if persistent, the damage to the engine will also occur. Thus, gasoline engines are limited in their efficiency by the inability of the fuel to smoothly burn in high compression ratio engines. However, the diesel engine is not subject to this limitation. It runs at high compression ratio. In part, this explains its high efficiency. It also runs lean, and its pumping work is low, further increasing its efficiency over the gasoline engine,
humankind needs quiet, smoke-free, and also odor-free diesel. So the next one is we need new cycles put into the practical, such as Atkinson cycle. So this has a smaller compression ratio than the expansion ratio, which means TC is reduced since the burn gas cool as they expand, making the cycle efficient. We throw away less waste heat via the exhaust. So the last one is run at the engine at optimum condition, meaning low friction and also low pumping work. Try to approach the pushing piston efficiency of 35%. This already is happening in some stationary piston engines, as for example, large slow piston engines used at pipeline compressor stations. So also this is an important characteristic of the engine used in hybrid gasoline electric vehicle. Let the gasoline engine in hybrid gasoline electric power plant only run with good throttle opening and also modest RPM. I think that's all for me. Thank you.